In this video, we will discuss dynamic efficiency and the proper allocation of depleting resources and how that pertains to sustainable development. We will introduce the two-period model, and by doing so compare static and dynamic efficiency allocations. We will briefly discuss scarcity, Hartwig's rule, and the effects of sustainability on our model. We will be using a two-period model to properly allocate a depletable resource between two generations. The two-period model we are using is a simplification of an n-period model. The strategies are the same, but the latter involves more calculation, and for the simplicity of discussion we will only use the two-generational case. For this model we will assume a constant marginal willingness to pay, also known as a constant demand between the two generations. The price and marginal cost of the depletable resource in question are shown here, where P is the price and Q is the quantity. The static allocations for two generations are shown here. Both generations receive maximized return when 15 units of resource are available and consumed. This is because this is where the price equals the marginal cost of the resource. This allocation is only optimal for abundant resources. If the resource is plentiful, then static efficiency criteria can hold true, regardless of the discount rate between the two generations. In this case, a resource would be considered abundant if the quantity was greater than or equal to 30. This is because both generations would produce 15, or consume 15 units of resource, since that is where the efficient allocation begins. However, this only works if there's more than 30 units between the generations, such that both can consume their desired amount without depleting the resource. Continuing with that thought, we can say that this model changes when the resource is depletable. If the supply is insufficient to meet the demand for both generations, static efficiency will fail to optimally allocate this resource. For the rest of this example, we will assume that the total supply of the depletable resource is 20 units. If the supply is 20 units, and we continue with the static efficiency model, then generation 1 will still consume 15 units. But then the supply is insufficient to meet both generations, and that will leave generation 2 with only 5 units to consume, which is 10 units below their static efficiency mark. This is far from an optimal allocation. If there is insufficient resource supply, we must shift from the static efficiency model to the dynamic efficient one. In this scenario, we will strive to maximize the present value of net benefits between both generations, rather than maximizing the present value of the first generation alone. We can relate the marginal benefit of the two generations by imposing a discount rate R. You can see here the marginal benefit in generation 1 equals the marginal benefit of 2 multiplied by 1 plus the discount rate, which we will assume for this problem to be 0.1 or 10%. The two-period model can be illustrated graphically by flipping the graph of period 2 such that the zero axis for the second period of net benefits is on the right side, rather than on the left. So on the left side over here, this is the marginal net benefit for generation 1, and over here is the marginal net benefit for generation 2. Down here, we have a box shaped or limited to the amount of resource available. So we have 0 to 20, and then 20 to 0. The one on top represents the quantity consumed in period 1, the bottom, the quantity in period 2. At any point on this horizontal axis, the sums of the amount of resource sum to 20, which is the resource constraint. By locating the point where the two generations both receive equal marginal benefit, this point here, we find the dynamic efficient allocation. In this example, we can see that generation 1 consumes slightly more than generation 2. You can see down here that generation 1 consumes roughly 10.2 units and generation 2 9.8. The price of the resource can then be found for both generations by using the previously defined price equations, shown again for simplicity's sake over here in the bottom left. When viewed together, the dynamic efficiency allocation looks much more fair to the needs of the second generation than the static efficient one. So previously, generation 1 would consume 15 units, which would be right around this point. So you can see that the value that they lose is shown in this little triangle that they lost here. But where generation 2 would have been consuming 5, they now consume almost 10. You can see a large gain in benefit here. So on this slide, we show the total net benefits by integrating the marginal net benefit curve. And this one shows the static efficiency model. You can see here there's a large gap where these benefits are not being received by either generation. By summing these areas, this triangle here and this trapezoid here, we arrive at the total present value of net benefits of $67.28. 45 of those dollars are consumed by generation 1, shown by the triangle here, and $22.28 are gained by generation 2, shown as the trapezoid over here. Now, with the dynamic efficient model, all possible benefits are received. You can see that we now fill in this region that used to be empty. The net benefits lost by the first generation are more than made up for the gains by the second generation. So here the total net benefits increased to $76.37, which is a gain of roughly $9.10. The present value of net benefits for generation 1 is $40. Should be shown right on this side, this side of the line right there. This is generation 1, generation 2. Generation 1 gets $40 and generation 2 gets $36.36. A $5 loss by generation 1 yielded a $14 gain in generation 2. You can see that it seems much more fair. Marginal user costs rise over time at the rate of discount, affecting efficient prices to rise over time and thus reflect scarcity. That's why the prices of the good in generation 1 are cheaper than in generation 2. But a higher discount rate will favor the present, as you can see here by a red line. This is an increased discount rate from r equals 0.1 to a larger value. The amount allocated the first period rises, the amount allocated the second generation falls. So you can see here is like the previous allocation with a discount rate of 0.1, and the allotment is almost the same. But if you increase that, the amount consumed by the first generation increases, and the amount consumed in the second generation decreases. Although the present value of net benefit between the generations was maximized, is this fair? A dynamic efficient allocation will not automatically satisfy the sustainability criterion, but can be consistent with sustainability. Sustainability criterion is shown here. It means that future generations should be left no worse off than current generations and perhaps be left better off. And the problem with the present value of net benefits is that generation 1 still receives more positive benefit than generation 2. But with a discount rate greater than 0, an economically efficient allocation will always allocate more of the resource of the first period than the second. The net benefits will always be greater in the first period than the second with a discount rate greater than 0. But the sustainability criterion can still be met if the first period sets aside a certain amount of net benefit for the second period. So we can return to this here. So you can see that the first generation receives about $3.70 more than the second generation. So if they were to set aside a certain amount of money, in this case, for generation 2, we could consider that optimally fair. So now we can continue on to Hartwick's rule. Hartwick's rule defines the amount of investment in produced capital, meaning knowledge or buildings or stocks, that is needed to exactly offset the declining stocks of non-renewable resources. So basically, as we consume natural resources, we can offset their capital by producing human capital. This investment is undertaken so that the standard of living does not fall as society moves into the indefinite future and constantly dwindling non-renewable resource stocks. Basically, physical capital should be able to substitute for natural capital. This is a very strong assumption to make. Hardwick's assumption seems like maybe a reasonable one as an achievable way to reach sustainability, but this type of sustainability is considered weak. It is based on the idea that human capital is directly substitutable for natural capital. Strong capital, on the other hand, is the concept that all human life and activity should occur within the limitations of the planet, and this does not allow for substitution between human and natural capital. Not all efficient allocations are sustainable, and not all sustainable allocations are efficient. Market allocations may be either efficient or inefficient, and either sustainable or unsustainable. Policy changes can produce win-win situations, because by correcting for a market inefficiency, net benefits can be increased. That was a brief overview of the two-period model and how to allocate a dwindling resource stock between two generations such that you maximize the benefit received by the two generations as a whole. This is not necessarily sustainable because the net benefits in the first generation will always exceed that of the second with a discount rate greater than 0. But it gives a good idea of how you should change your consumption patterns to compensate for the future needs of later generations.